Okay, now let's take our regular simple attention mechanism and create a simple weighted attention mechanism with three tensors, one corresponding to a key, another a value, and then the query tensor. All of them will have trainable weights and will eventually go into the transformer block that we are trying to create. So I'm going to start with a new notebook, and then I'm going to save that as a new file. So be 06 simple weighted attention mechanism. And yeah, cool. So I'm going to just, is there a way I can select the kernel? Okay, so I'll start us off with some markdown. So just kind of just turn this into markdown. Okay. So title this with simple weighted attention mechanism. Whoa, that's big. Okay. So first off, let's get some dependencies. Okay, so we'll need in this case torch, just torch for now. And then what we're going to do is we're going to set the manual seed again to 123. Okay. And then we're going to define the context that we were using last time. Let me just get rid of that. So the context last time we used was this one here. And we can just kind of copy that and paste it into this area here. Nothing else changes. Then let's just kind of make sure that we have the right thing. And we do. So we have 6 tokens. So our context here, at least our context window is 6. And then we have pretty much an embedding dimension of 3. Okay. And so we'll also need to create trainable weight tensors or weight matrices. And basically, they're just, like if you read the book, they're just normal tensors with dimensions d sub in, d sub out. Basically, that dimension is our the embeddings right here, right? So it'll be like 3 in, 3 out. We can do it that way. So we can define d to be context is 0 dot shape, and then we can just output d. So yeah, so that's 3. Okay. Yeah, so let's title that with weight matrices, weight tensors, I guess. Let's create w query, w key, oops, and then w value. Okay, so our goal is to create these 3 tensors that will be trainable. So we can just define something like d in is going to be d0, d out is going to be d0 too in this case. Okay, and then we can just do d in, d out, see if we got that right. 3 3. Cool. Now let's create those 3 tensors, right, with random values, initialize with random values, because we're going to be training these weights eventually. So initialize the weight tensors with random values. So that's like the whole point. So here we can say w query torch.rand, right? D in, D out. W key is going to be torch dot rand, D in, D out. Okay. W value is going to be torch dot rand, D in, D out. and then we'll just kind of output that as like a tuple or threeple. W query, W key, W value. Okay, so now we have our three tensors. Now these are technically trainable at this point. So how do we actually start doing all these calculations? Well, remember that basically we're doing matrix multiplication. So what we want to do is, like, let's say we want to calculate again the context vector of the second token, right? Journey. So that would be at like context 1, for example. So we can say context 1. Okay, that's like the second token. So we can call that query sub 2. Okay. So, oops, I should probably output that too. Okay. So this is the one that corresponds to journey. So then what we want to do is we want to basically do matrix multiplication against the key and the values to get the corresponding key value, right? So, and if you look, so I have like Sebastian's notes up from his repo. So basically, like, the goal is to take one of these tokens, right? In this case, journey, and we got like 0.5, 0.8, 0.6 as we have shown here. I think he just did some rounding. But basically, you want to pass this into the query key value weights, and then you'll get back basically Q2, K2, V2. We'll call them query sub 2, which we already have. We also have this one called key sub 2 and then V sub 2. Well, actually, we'll reassign this. But yeah, so then I think there's a little bit more to it right here. So this is the operation that we're trying to implement here. So actually, I named it incorrect. I should have called it, instead of query sub 2, I should have called it x sub 2 as like the input sub 2. So let me actually just fix that. Here, I'll call this x sub 2. X sub 2. Okay. And so we want to just basically do this multiplication here. Basically pass it in like this. And then we'll get back 3 results. So in this case, we'll have query sub 2 is going to just be x sub 2 at w query key sub 2 equals x sub 2 at w key, and then value sub 2 is x sub 2 at w value. Then we can just kind of return that as a tuple. See what we get. Cool. So we have stuff. Basically, I think this is right. Given that as long as we had set the manual seed, should match close to what we expect. So basically, we have 3 tensors here. This one corresponds to query sub 2. This one's key sub 2, and then this one is value sub 2. Okay. Okay. Next, the next thing here is we need to now take this concept, right? Like, this is just for like one input, but what we need to do is we actually need to do this against, like, take that one input and then find all the other corresponding inputs, like the keys and the values based off of that. So in his notes, he actually then runs through, I think this is unnormalized. Yeah, he runs through the entire matrix, right? Against the key and the value weights, and then he gets matrices out of that. And I think after that, what ends up happening is that he takes this query 2 here, and then he matrix multiplies again against the transpose. You see t here. This is like he's gonna multiply by the transpose of this matrix. Okay. Yeah, I think that's what he ends up doing. So let's just try to emulate that. So in this case here, against all matrices, so do it against all other inputs. Do the same thing for all the other corresponding inputs, right? We're going to do keys, so just generalized. It's going to be the entire context, matrix multiply with W key. Then we'll have values is context multiplied by the value, and then we should get keys and the values. Okay, so we'll take this here, and what we're going to do is we're going to transpose keys and multiply against query sub 2, which is like the result of our input matrix multiplied by the query tensor, that weight trainable weight tensor, and we'll get back the attention scores just for that specific input against query 2. So we can call this like attention scores 2. That's going to be query sub 2. Matrix multiplied by the results that we got here, this keys here, transposed. So then we can just output that, attention scores, and then we'll have a nice vector. Okay. Next, what we want to do is we want to normalize this thing, right? Like, so we want to turn, remember, like attention scores are like unnormalized. So what we need to do is we want to turn these to attention weights. So then we can just do a softmax again. Okay, we'll do a softmax against the attention scores. In this case, with this single vector here, we just apply softmax with attention scores 2. However, on the last dimension too. But however, in what Sebastian did was he also has this. In this case, where did it go? He has this. He divides them by the square root of the embedding dimension d sub k. So it would just be d sub k square root. Okay. Don't really remember the reason why, but here we just want to get to the point where we have ttnn. So I'll just do torch softmax attention scores 2 divided by the square root of our embedding dimension. In this case, our embedding dimension was 3, so we could just do in this case d sub in, d sub out. It doesn't matter, they're the same value. So we'll just say d sub k is going to be d. What did I define it to be? D sub in. Okay. I just call it d sub out. Okay. So now attention weights 2 is just going to be torch.softmax attention scores 2 on the last dimension. Okay. And then we're going to have to modify this. We're going to have to divide everything by d sub k, but it's going to be the square root of that. Okay, so now we have the attention weights that is normalized. And I think if we were to see this here, all of this should add up like close to 1. Let's see. So attention weights sub 2 sum. Yeah, 1. This is hard to tell from here. But yeah, it should add up to 1 because these are like probabilities at this point. Okay, finally, remember to get the context vector as we did back here. Where is it? The context vector is just basically the attention weights multiplied by the context, right? But in this case here, we're going to multiply that by the values. So if we look back here, he's going to do attention weights matrix multiplied by the values to get the context of vector. So we can just emulate that again. So context vec 2. So the context vector for that second input is going to be attention weights 2, matrix multiplied by the values, and we'll get another vector. So that's the attention weight for the second input, right? 0.6856, 10544, 11388. Okay. All right. Next, we want to just generalize this over the entire context. So in this case, we just go mark down up here, generalize for entire input context. So it's just taking that context vector as x in this case. So x is going to be context, so that this entire matrix up here, right, is going to be basically your input batch, right, your input. So let's just say x batch, because inside are the inputs. So we'll just do the math again. So we'll have keys. So this time we call it keys because it's using the entire context. So we'll just do x batch, matrix multiplied by w key, so that trainable matrix. Queries is going to be x batch, matrix multiplied by w sub query. Then we're going to have values. It's going to be x batch. It's going to be matrix multiplied by w sub value. Okay, so we have the keys, we have the queries, and we have the values. Next, we're going to have to get the attention scores again. So this time it's generalized. So we're just going to matrix multiply the queries as we did up here with just a single one right here, right? With the keys transposed. So keys transposed here. So we'll just matrix multiply with the keys transposed. Then we'll get the attention scores. Now we need to normalize the attention scores by getting the attention weights. So then that is just a torch.softmax attention scores divided by d sub k square root, and we should probably define that again at the last dimension. So let's define that up here. D sub k equals d sub out. Okay, so we have the attention weights. It's normalized. Let's get the context vex. Okay, all the context vectors. So that's just basically the attention weights. Again, like before here, matrix multiplied by the values. Okay, and we will have all the context vectors. Okay. It's kind of hard to tell like if it works yet, but we will know soon enough. So this is basically the simple weighted attention mechanism. So it's more advanced than the simple attention mechanism. Now things are weighted. So let's try to do the ttnn version. So we'll just like kind of just simulate the entire thing again, or rewrite the entire thing, but this time with ttnn. So let's turn this into Markdown. ttnn implementation. Okay, so from here we're just gonna do the exact same thing that we did. I wonder if it's worth doing some of that tracing again. Yeah, you know what? Let's do that. Let's do some of that tracing again. Okay, so we'll do import OS. Wait, this is Markdown. How do we do this? C? Right? Or hit arrow. Okay. We'll import OS and we'll set the environment variable again. So in this case, it'll be os.environ ttnn config overrides. It's gonna be that JSON again. So try to get this right. Enable fast runtime mode. And that's gonna be in this case false. So we'll run that. And then let's actually see if that is correct. So os.environ.get ttnn config overrides. That should get us the right thing here. Cool. All right, so let's do the same thing again. We're going to import torch. This time we're going to import ttnn. And we'll need that tracer code. So from ttnn.tracer, import trace, and visualize. So that we can visualize the flow of everything. torch.manualseed as before. Okay, we'll set that to 1 through 3. And then we're going to redefine that context so just so that it's easier to do things. See it. So we'll copy and paste that here. Cool. And again, just context.shape to make sure we got everything right, and we did. Okay. So now let's, again, the goal here is to create the query, key, and value weight tensors in Torch. Okay. And then we can create the ttnn tiled versions using ttnn from Torch. Okay. So we need to kind of make sure that they're tiled and that they are in the device, so that we can actually do the matmul, the ttnn.matmul operations, because ttnn.matmul, as you remember from the earlier notebooks, that the ttnn tensors actually have to be in tiled layout and also on a device for that matrix multiplication to work properly. But we're not there yet. Let's do that conversion first from Torch, and then we'll do that matrix multiplication in another cell. All right, let's get started on that. So again, let's just define d to be context 0.shape. So basically the shape of this first batch here. Okay, I think this one doesn't matter. So we'll say dn is going to be d0, d out is going to be d0, and then let's just, for sanity check, output that. Okay, 3 again, and let's just convert our matrices. So we'll have context ttnn. So that's going to be the Tenstorrent version of our context, our input. So it's straightforward. ttnn dot from torch is going to be the call. Give the context. Make it bfloat 16 type. Okay. And then convert that layout to strided in Torch, but now it's going to be tile layout in this case. Next, we're going to create our query, key, and value matrices. We're going to initialize them with random values, given that we already have manual C1 through 3. We should get close to the same values as we had before. The reason why I say close is just due to the fact that Torch does float 32, and then here we're operating on bfloat 16. So just create the random matrices again. W key torch.rand d in d out. W value is going to be torch.rand d in d out, and then we're going to take these matrices here, these tensors, matrices, whatever, and then we're going to turn them into ttnn versions. So w subquery ttnn is going to be ttnn dots from torch. Okay, we'll take w query as the input, the torch tensor that we want. D type is going to be bfloat 16, and of course the layout is going to be a tile layout. It's the only way it'll work. Now we do the same thing for all the other ones. So w key will be here. D type, I should type better. D type is going to be bfloat 16, and then layout is going to be tile layout. Okay. W value ttnn. ttnn from torch. W value d type ttnn dot bfloat 16. Layout is going to be tile layout again. And then let's actually output to see what we get from here. So w query ttnn, w key ttnn, and then w value ttnn. And notice how we're accessing the hardware now, or we want to initialize ttnn library to do that. So we have a bunch of these tensors now. These are randomly generated. Notice data type bfloat16, layout tile. Then we can also just visualize the same thing here too. So we could say, since it was traced, we could say visualize wquery ttnn, visualize w key ttnn, and then visualize w value ttnn. And we'll get like an output graph here. So I think this one's actually the context. So far, so simple. We're just creating a bunch of ttnn tensors from the torch tensors. Okay. Next up, what we want to do is, I think we'll try to send them all to the device, and then we're going to perform our operations. Let's do it a step at a time. Let's just open up our device and then send these ttnn matrices that we've just created, the wquery, the wkey, and the wvalue ttnn tensors to those devices, and we'll kind of just map what they look like here. So device ID is going to be 0. That's going to be our device that we want to open up. Just realizes, should I make that font just slightly bigger? Let's do that. I was trying to customize my computer a little bit more. Okay, that looks better. Okay, so device ID is 0, so we can say device equals ttnn.openDevice. We'll say device ID. So we're going to grab a handle to the device again. Okay, and then at this point, the device is ready. So if we do this, we've opened the device and it's all good. If we say, if we see that there's chip detection complete found, that's a good thing, right? That's a good thing. So let's also have like another cell down here to close the device, because that's good practice. Okay. So whenever we're done, we're going to execute the cell, and then we've cleaned up. So again, with trace, let's just see what it looks like when we send our tensors to the device. So context ttnn is going to be ttnn to device. Okay, we want to send a context ttnn tensor currently on the host to the specific device. At this point, what returns back is actually the ttnn tensor that is on the device. Okay, so this one originally was on CPU, then we transfer to the device, we get back the reference to that specific tensor on the device. So wquery ttnn is the same thing, to device. It's going to be wquery ttnn device, then wkey ttnn.to device, wkey ttnn device. Finally, wvalue ttnn.to device. It's kind of repetitive, but it's good to get used to the API when you do it like this. Okay, so now we've moved all of these things to the device. So that should be easy enough. And then let's actually visualize what all that looks like now. So visualize wquery ttnn. And then let's just kind of do that 3 times. Let's just edit that. Value key. So at this point, we have a little pipeline going on. So let's take a look at that. So we start out with some random matrices. Okay. We convert them from torch. So notice how this torch.float32. We get back bfloat16 tile layout tensors, but then we're going to call ttnn.to device to send these tensors. At this point, they're in the CPU to the wormhole card that we have, the device. And notice how memory here says DRAM interleave. So that's how we know that things are now sitting in the wormhole, pretty much. Okay, so Let's add more code down here, and we're going to do our compute. So with trace, let's try to do some compute. So goal right now is to be able to basically perform the same calculations as we did all the way up here, right? So we're gonna multiply our context ttnn with w key, w query, and w value to get like keys ttnn, values ttnn, and then queries ttnn. At the same time, we also need to also grab a ttnn version of the transpose of key, and I'll show you how to do that with some API called permute. And then yeah, that's after that, then we just basically perform the softmax using ttnn, and then get the context vectors by using matmul again, and that I think that's it. So let's do that here. Okay, so let's calculate w no, not w, let's calculate keys ttnn. So keys ttnn is going to be ttnn.matmul context ttnn. In this case, that's like the x, right? And then we're going to pass in the key ttnn version, the weight matrix corresponding to keys, and then we'll do the same thing for values and query. So ttnn.matmul context ttnn w value ttnn, then queries ttnn.matmul context ttnn w query ttnn. Okay, so let's see what that looks like. Keys ttnn, values ttnn, and queries ttnn. Oh, lots of logging. So we have all these results here, and then let's visualize that. So visualize keys ttnn, for example, and I think yeah, it just shows everything actually I learned just now. So okay, so what are we looking at here? That's weird. Oh, did we only matmul one of these? Let's see. Oh, cool. So maybe no, it does. So it does show only the keys matmul. So at that point, so let's actually visualize values ttnn. What do we get here? Oh, that's cool. So it just kind of just draws on top as we do this. Okay, fine. Let's do everything. Okay, great, cool. Okay, so we do need to visualize everything because they stack. Okay, so this one corresponds to keys, this one corresponds to values, this one corresponds to queries. And you see here that this one is the context and how we are multiplying context and the matrix here, the key matrix, to get, in this case, keys ttnn. This one's keys ttnn. Yeah, that is keys ttnn. And then we basically do the same thing with this one here is the value, w value ttnn. We basically then get the the values ttnn. But this actually looks not correct. I think my matrix multiplication is wrong. Maybe I was just blindly typing. To device, no, context ttnn. So value context ttnn, okay, multiplied by w value ttnn. So that is, we're multiplying the context, but then this one here looks like we're using the wrong thing. Oh, I messed up. Wow, that's interesting. This one is 3, so that's the w keys. So this one's the context right here. Okay, I looked at it incorrectly. It's a different order. Is it because we defined it in a different order? Let's see. Okay. So that is the reason why this arrow spans across all others, because we're referencing this. This one is the context, and then this one is this one's a key value query, and then you'll get back these results here, which is going to be the keys ttnn, the values ttnn, and the queries ttnn. Okay. So now the next challenge is basically how do we transpose, right? Transposing a tensor, a ttnn tensor. So that is available API for us to use. So let's add some markdown. Transposing a ttnn matrix tensor. I keep saying matrix. Transposing a ttnn tensor. Here is, we can use ttnn.permute to transpose a, in this case, ttnn tensor. Okay. Okay. So how does that look like? So we have to transpose keys.t, right? So in this case, or keys. So here we need to be able to take keys, which is in this case keys ttnn, transpose that, right, to get this equivalent result in torch here. So we can call this keys transposed ttnn, right? We can just say ttnn.permute. In this case, we can say keys ttnn, and then the second argument is basically the shape, like like which dimensions will now fall into that position. So in this case, we want to swap the first dimension with the 0th dimension, so we do 1, 0 this way. Okay, and we do that, we get the transpose here. See, it says 6, 3, and before, or sorry, 3, 6. Before it was 6, 3. Okay, so now we are getting 3, 6. So we have transposed the matrix. So now we have to make use of that. So let's actually do a with trace too. Okay. This is now, in this case, a separate matrix. So if we visualize, keys transpose ttnn, right? We have this new one right here. So this is going to be the output of permute. So 3, 6. Okay. Now, how do we make use of that? Well, again, how do we? When do we use that? Right? We use that to get the attention scores. So with trace again, we'll try to figure out the attention scores ttnn version. It's going to be ttnn.mapMul. It's going to be multiplying the queries ttnn against the keys transpose ttnn. And then what we want with these attention scores ttnn is to make an attention weights ttnn, right? And we had to apply that one scaling, if you recall. So let's actually compute that scaling first with the attention scores. So let's, we're going to break down this operation here into, the softmax against this one is kind of tricky to type. So let's actually create an attention scores that looks like this first, like an attention scores ttnn scaled, and then pass that into our ttnn softmax. So what I mean is, I can just say attention scores scaled ttnn is just be ttnn.divide the attention scores ttnn by d sub k square root of it. Okay, and then we'll find the attention weights ttnn dot softmax will be attention scores scaled ttnn across the last dimension. Okay, at this point, let's see what we get for attention weights. We don't really care about the attention scores anymore because we're not going to really use that. ttnn. So we'll have this one here. So 6 by 6 now. And if we visualize that, we'll see, okay, that by multiplying our transposed keys, where's the permute? All right, here, this transposed one here, okay, against our which one is this one? I think this one's the values, right? Or no, queries. Where is it? Queries. Yeah, the queries and transpose will get the attention scores ttnn, which is this one right here. Then we normalize it, okay, by scaling it, or not normalize, we'll scale it, then we normalize it with softmax here. Okay, so now we have this one matrix here. What do? We're going to compute the context vectors. So we'll have with trace again, just to see. Context vex ttnn is just ttnn dot what is it? Mat mul attention weights. Oops. Weights ttnn with our values ttnn. Okay, and then we'll just output that. We'll see what we get, and we'll get this one here. Let's visualize, see what that is. So going back, let's review. Attention weights ttnn is the softmax normalized version of the attention scores all the way. Sorry, lots of stuff. All the way where at? Here. Okay. So softmax against the scaled version across the last dimension. We'll do a mat mul against values ttnn, and we'll get context vex ttnn. We'll get this one here. Okay, so just to visualize what that looks like. So where is the softmax one? Okay, so this one is the attention weights going into here. This one all the way here is basically the values ttnn. Okay, so we have a big computation graph. So values ttnn all the way down as input here. This one is the attention weights. What comes out of it is going to be the context vex ttnn, but notice how it's still on the device, so we should transfer it back. Context vex ttnn is going to be ttnn.from device context vex ttnn, so that transfers it back to host. So if we do with trace again, we'll see just that. Right, so let's do visualize context vex ttnn. Okay, so yeah, it goes from DRAM back to normal CPU tile. Okay, let's clean up. We have what we need. Both are in CPU, and so what I want to do here is I want to show like a comparison between what we got in Torch and what we got in our hardware. So if we still have it, I think we still have context vex. Okay, and then we also have context vex ttnn. Okay, so they are almost similar. It's very close. So they both have the same shape, that's for sure. So I'd say that is good. Let's see. I'll say that for next time. So there is a way to compare these things to really make sure, but let's keep that for next time. But basically, this is the pattern for a simple weighted attention mechanism. Yeah, let's keep that for next time. But this is like the basic thing, and then we're going to generalize this into like its own class and things like that too. So it's a good start. Let me commit this. simple weighted attention mechanism. Alrighty, see you next time.